Yeah, thank you for having me. It's wonderful to be here, and it's also great that I can come here by a train instead of having to take a plane at this time with all this situation going on with the airports. Yeah, so today I'm going to be talking about some future collider searches for new physics, and I'm going to emphasize some searches using a new type of potential collider called Wakefield colliders. And I'd like to just kind of start off with a more general discussion of what are the possibilities for future colliders. And I don't want to make it like a political discussion. I don't really have a dog in this race, necessarily. But I think it is something that's very interesting and something that will define maybe the next century of particle physics. So what are the possibilities for future colliders? You can pick your collider based on what particles you choose. If you have electrons and positrons, you have to choose a shape. If you do a circular collider, you might get something like FCCE, but there's also a lot of linear collider options. You can also go down the proton route for something like FCCHH, and also there's potentially a muon collider if you can make muon cooling work and some other additional challenges. And so at the end of the day, when you're choosing a collider, there's a couple of different things that you have to consider. There's the physics, which can be described relatively simply just with the particles you're colliding, the center mass energy and the luminosity. But then there's much more challenging questions such as the costs, the technology, and the politics, which is typically what really decides whether a collider is built. And so for example, here I'm showing a picture of the superconducting supercollider, which is magnets, the dipole magnets of the superconducting supercollider, which is famously a collider that was never actually built, despite the fact that it was potentially a tremendous benefit to the particle physics community. And it failed mainly because of these aspects here. I won't talk too much about those aspects because it's not my specialty, but it's something we always have to consider with these types of future colliders. And so this is currently in a museum, and so even though it didn't get built, it does give us some historical reference of how to actually build future colliders, and I'd like to actually get started with some of that historical reference. So here I'm showing a plot from Barger and Phillips, which is the available center mass energy of different colliders as a function of the year in which they were built. And you see, as a function of time, there's exponential growth in the energy that's attainable at these different colliders. And there's an obvious statement that you can make, which is the statement that discovery correlates with technological advancement. So for example, if you look at from 1930 to roughly 1950, this is the cyclotron era. And then you can see there's a knee, at which point there's a significantly faster growth, which is the synchrotron era. And then finally there's the collider era, which happened in roughly the 70s and led to the discovery of all of our known fundamental particles, or most of them. And so if I zoom in on this era, you can see that the current colliders have a trend that looks something like this. And what I like to do to understand this is I'd like to compare this with the mass of the fundamental particles that have been discovered as a function of the year in which they were discovered. And you see there's a direct correlation between these two different plots. So this is just an example of the obvious statement that technological advancement leads to discovery. So if I look into the future now at proposed colliders, there's a handful of different proposed colliders. There's, for example, the HLHC, which hopefully will happen in the next few years. I think it will. I mean, of course it will. I don't know. Then, if I go further into the future, there's some proposals in China like the CPC and SPPC, as well as the FCC. And then here I'm showing both the energy as a function of the year in which they're built, and also the luminosity as a function of when they're built. And I would like to point out a few trends here. So first off, using proton colliders, it does seem like the growth in energy as a function of time in which these colliders can be built is leveling off. And this is something that we saw with the cyclotrons and synchrotrons, right? That you can only take a certain technology so far before you start getting diminishing returns. Luminosity, on the other hand, is continuing more or less exponential growth in a very interesting and exciting way. And so I think one question that you could very seriously consider is luminosity a path to discovery? Alternatively, you might still have hope. After all, higher energies mean smaller distances, and we want to go there eventually. So is there an alternative to getting to new energies, maybe a leptonic path, such as a muon collider?
The plots are a little bit unfair, right? You've selectively kept some and not others.
That's.
I could probably turn the.
What am I missing?
Well, you include the ISR and the SPS on the left plot, but you drop them on the right plot and things like
Oh,
that.
they're on the right plot.
No, but I mean this curve, the curve he's trying to fit
Ah.
is all. Anyway,
Oh.
it was
Yeah,
just
yeah.
a wisecrack.
Okay,
Go
okay.
ahead.
No, but I mean, you're definitely right. And you know, these plots are just schematic. I mean, at the end of the day, these things happen over time. There's been improvements, and it's not meant to be anything more than schematic. But these are the two possible paths. One path is the luminosity direction, and this is a direction that I find very fascinating. I've written some papers on this in the past. So one thing I found interesting was whether you can actually search for SUSY using luminosity, using high precision measurements. And it turns out that just by looking at corrections to standard model observables, for example, here, does this have a, so here I have leptons and electroweak inos showing up in a loop with a Z boson. And since the FCCE is able to produce roughly 10 trillion Z bosons, you can measure Z physics extremely well and set competitive constraints on the parameter space of electroweak inos and leptons.
So you have like split supersymmetry in mind?
Not necessarily, but I think you're saying like high scale SUSY or
Yeah.
some analogy of that, yeah.
Well, the x-axis is not split, Susan.
Yeah.
Great.
So I don't have any specific SUSY parameter space in mind here. This is just,
Right. Okay.
But this is more like generic fine-tuned SUSY, right? So
Yeah.
that's
so
meaning
this
that
is not
MSSM
generic.
generic fine-tuned MSSM, right? That's
Yeah, yeah. Yeah, fine, yeah, you can say that as well. There was a follow-up study by these folks here which do something I think that's very fascinating, which is to look at stops and Higgs-inos. And what they find is that if the Higgs-ino is lighter than the stop, you can actually constrain stop quark masses up to roughly 6 TeV. And this is very exciting because if you know the MSSM, you know that the Higgs quartic coupling is actually calculable, which means that the Higgs mass is calculable within the MSSM. And if you take the observed Higgs mass, which is higher than it was originally expected to be, you can actually get a rough prediction for the stop quark masses, which is above what is currently constrained at the LHC, typically. And so getting up to 6 TeV is actually very exciting. I think we're actually finally, potentially, constraining some of this parameter space consistent with the Higgs mass. Okay, but I won't be considering the FCCE in this talk. I'll be considering the high energy direction, in particular through Wakefield colliders. So I want to consider this possible path to new physics using some new technology to get to higher energies in a significantly faster way. And okay, so whenever you're talking about new accelerator technology, I think a lot of people are very skeptical, whether it's muon colliders or Wakefield colliders. They think the challenges are just too immense. But I think it's worth having a historical perspective on this as well. At one time, it was thought impossible to even do a collider. Two particles, colliding against each other. It was thought you could only do fixed target experiments. And so Gersh Böttger, who's one of the fathers of colliders, famously said that the problem of colliding two particles is about as complex as that of arranging a meeting of two arrows, one of which is shot by Robin Hood from the Earth and one of which is shot by Wilhelm Tell from the planet revolving around Sirius. And I think that's an exaggeration. Of course, he said this after he succeeded in doing this, so I think he was trying to get grant money, most likely. And I'm sure he succeeded with that statement, but I think it's just generally true that a lot of times things seem impossible until they're not. And so with the P5 and the European Strategy Update, plasma Wakefield colliders have been an aspect that they've been interested in. The main goal is that they want to get to 10 TeV part on center of mass colliders, and this is one possible route that is under consideration. This is just another plot that I'll just show very quickly, is that the cost of colliders is increasing dramatically as a function of time. And the hope is that maybe you can build a collider that doesn't cost so much money, but I don't know.
But as a fraction of GDP,
Yeah, but it's a
it's
fraction of GDP.
not increasing that much. Right? It stays
Oh, I
constant.
see.
That's what I.
So this is in 2026?
But GDP grows much faster than inflation.
Okay, I see, okay. Maybe I shouldn't show economics plots then.
I don't know if I think it would,
Yeah.
it's an important.
I think it's an important point to make.
Right, what fraction of your economy are you dedicating to this, right?
Okay, next time I give this talk, I'll divide by GDP.
I mean, they're both relevant.
Yeah. Okay, so let me get into my actual talk. So what is a Wakefield accelerator? I need to explain this first. So current accelerators use radio frequency cavities. So it's just an electric field which is oscillating back and forth. You shoot a particle beam at one time. It feels an electric field and gets a kick. But the current superconducting radio frequency cavities have a maximal electric field that's possible, which is roughly 100 megavolts per meter. And this is limited by the fact that once the magnetic field inside of these cavities gets too large, it starts breaking the Cooper pairs inside the material, and you no longer have a superconductor. So that would be a problem. However, plasmas do not have such a problem, and theoretically, they can generate electric fields up to 1,000 times larger than the best superconducting radio frequency cavities. So this is a picture, a simulation of what this would look like. So the idea is you have a plasma, which is shown here in blue. You shoot in an initial beam, which might be a beam of particles or a laser, and this will create a wake within the plasma. When you have that wake, you can send in a secondary beam called a trailing bunch at this point, and it will see the higher density of electrons here, which will create an electric field, shown in this black line, which gives this bunch a kick, potentially up to 100 gigavolts per meter. And so this is really the basic idea. It's quite simple at the end of the day. But this is all very complicated to actually achieve in an actual accelerator. So first off, let me just kind of discuss the history of this. So it was originally discussed in the 70s and 80s as a potential way to improve accelerators. People first started developing proof of concepts in the 90s, but there was really a big kick in the early 2000s where they were actually achieving substantial gains with Wakefield colliders. So for example, there was 100 mega electron volt acceleration at LBNL in 2004, and then a 43 GeV acceleration at SLAC using a plasma Wakefield accelerator within just a few centimeters, 100 centimeters. And then recently there's been additional progress as well. And this progress has been made by many different labs across the world.
Is that still the record in 2006, or have people gone beyond 43 GeV?
So this is, okay, so this, I think this is the record more or less, but it wasn't a very high quality acceleration. Basically,
focused on the quality instead.
Yeah, so let me go into that in a little more detail. So one thing
Sorry, that's what I was good. The idea is that you do this acceleration in plasma, but then the particles exit the plasma and collide in vacuum, right? Because you don't want to collide in plasma.
Yeah, so this is just the acceleration stage.
Uh-huh.
And then you collide in the detector in the vacuum, not in the plasma.
Is there a scheme to link them together? Because 43 GeV isn't very interesting.
Yeah, so you need to stage this, and this is one of the main challenges. This has not been demonstrated as far as I'm aware. LBNL is currently trying to demonstrate this. They're trying to do 2 stages. But at the end of the day, if you want to get up to 10 TeV, you'll need hundreds of stages. And so this is one of the main challenges with plasma Wakefield accelerators. There's several challenges, but this is one.
So there's some kind of engineering limit on a single stage's energy, like max. Like somehow we can't push it above like 50 GeV or something.
It would be hard to push it above, but luckily you don't have to. I mean, you can just do it 100 times.
Yeah, well, if you can make it work.
Yeah, if you can, but yeah, in theory you can't go too much above this.
But what sets the energy limit in a single stage?
Yeah, so as you make the energy that you get is related to the density of the plasma. The density of the plasma also affects the size of the wake. So it turns out that the energy you get is inversely proportional to the size of the wake. Okay. So it just gets harder and harder to accelerate these beams. That's one aspect. So there is a limit, I guess. Okay, good. So one thing I want to emphasize is that there's been significant progress, both in making high quality beams and high energy beams, but not simultaneously. So here what I'm showing, and let me just describe this plot. So this is a plot of the energy of the driver beam and the trailing bunch, both in the situation where there is no plasma, in other words, when there is no boost, and in the situation where there is a plasma. And so what you see is that the trailing bunch here does not get affected, but here, when there is a plasma, it gets a boost by roughly 50 mega electron volts, which is not very much, but the important thing here is that the beam has relatively high quality. So the description of that in this particular plot, or one description, is the energy spread, and you see that the energy spread of this beam is not very different than the energy spread of this. And as a function of time, the energy spread has decreased almost exponentially, and we're getting to the point where it's almost ready for a collider. However, this is not a whole lot of energy, and so you might ask the question, well, can you get high energy accelerations? And here is one result from 2004 at LBNL, and there's a lot of different plots here trying different plasma configurations. The important bit here is that you can actually get roughly of order 10 GeV acceleration to a beam in only 30 centimeters for certain configurations. So this is a pretty good gradient. This is roughly 30 GeV per meter. So that's on the order of 100 GeV per meter that I was mentioning before. So you are getting close to the collider goal that you would need for energy acceleration, but these things have not been achieved simultaneously. So you can either get a high quality beam or a high energy beam, but doing so simultaneously is still a challenge. And then there's other challenges such as, okay, I'll skip that for now. There's other challenges such as staging, as well as getting these beams to go through the accelerators with a high frequency. So the plasma has to recalibrate every single time you accelerate it, and getting to a high frequency in order to get a lot of collisions is also quite hard.
Sorry, I don't know enough about collider technology, but are there existing technology that we can use to improve the quality after it's being accelerated, for example? I don't know.
So you can modify the beam in many different ways.
Yeah.
But if you lose a lot of the beam,
Oh, luminosity. Okay.
yeah, then you're gonna miss out. So you can't lose it. You also can't have too much of an energy spread because these things grow geometrically. So yeah.
Is the additional energy, if I were to stage these things, is it natural that I should think that the energy is additive?
Yeah.
It is, so it's, if I get 10 GeV in this section, then the next section I put it in, I'll get 10 GeV also.
Yeah. So then you would need 1,000 sections, and then you're at.
Okay, so it's not in principle, it's not diminishing returns, at least not immediately.
Yeah.
Don't I have some kind of barrier, right, between the different stages, I would think, to keep the plasma isolated.
Yeah, you do need you need them staged and separate. And separate.
But you don't lose any energy sort of passing through. There's some slab of material at the end of each. I guess.
Yeah, that's not necessarily a huge problem. Okay. Good. So so for my talk, there's a lot of technical challenges with these plasma Wakefield accelerators, but there's two that I really want to emphasize because they matter for the physics quite a bit. So one is that in general, it's actually a lot harder to accelerate positrons. So as I mentioned, you can put electrons here, and then you'll simultaneously get a kick, and it'll also focus the beam. However, if you want to do this with positrons, if you put positrons here, they'll get a kick in the wrong direction, so you can't do that. So you'd have to put positrons, for example, here. But then the challenge is that this will, in general, defocus the beam, just because they'll want to go like this. So it turns out that accelerating positrons is significantly harder, and it's not known whether you can actually do this. It's a huge R&D effort to actually determine whether that's possible or not. The second challenge is that, for reasons that I'll explain in a little bit, there's very large beam-beam interactions at the collision point, and this significantly alters the physics that you receive, as I'll discuss in a bit. But so, one thing that you might be asking is, why don't we consider large beam-beam interactions at other colliders like the LHC? And so to do that, I'd like to actually just discuss what collider beams look like in general. So at the LHC or HLHC, you have bunches. So each one of these is a bunch. A bunch looks something like this, where there's roughly 10 to the 11 protons, and the bunch is quite macroscopic. It has a longitudinal length of roughly 50 millimeters and a transverse direction of roughly 10 micrometers. And there's roughly 3,000 of these bunches going around the ring in opposite directions, and then they collide in an interaction point with a frequency of roughly 40 megahertz. At a muon collider, you would have one bunch because you're limited in the number of muons that you can produce, but the same thing goes forward. You have a smaller longitudinal length, and you have a much smaller transverse length in order to get high.
Is this in our frame? These are the dimensions in our frame?
Yes. But for a Wakefield collider, there's several challenges. So first off, there's the crossing frequency, which has to be significantly lower. This is actually quite a challenge because you have to have the plasma recalibrate every single time you accelerate a beam, and roughly you can only get to 50 kilohertz. There's also a challenge in the sense that you can't fit so many particles in here. The goal would be something around 10 to the 9 particles. And so in order to get high enough luminosity, you need to squeeze the beam to roughly 1 nanometer. So this is very challenging. So just to summarize, the beams can be quantified in this way. So if the LHC beam looks something like a blue whale, the plasma Wakefield beam has to be roughly the size of a beam. So it's a huge, completely different type of beam. And in order to get the correct luminosity, you need a very large number of electrons within this bunch, a high frequency, which is very challenging, and a very small transverse length. All of these parameters affect a second quantity, which is the beam-beam interactions. And so the beam-beam interactions can be quantified in this way. So this parameter, called the beamstrahlung parameter, is just the electric field as seen in the rest frame of one of the electrons as the other beam passes by. And parametrically, it scales with the energy of the beam, the number of particles in the beam, and the longitudinal and transverse lengths in the following way. So for the LHC, all of these numbers, if you plug them in, this is completely negligible. For a muon collider, it's also negligible, but slightly more significant. For a Wakefield collider, it's of order 10 to the 5. And just to give you an idea of what this means, 10 to the 5 corresponds to an electric field as seen in the rest frame of one of the particles, which is large enough to do Schwinger pair production of muons. So this is pretty insane. No electric fields have ever been produced even near this value. In fact, this is so high that we don't even have a calculational tool to actually do strong field QED in this regime. So for the simulations that I show of beam-beam interactions, we'll actually be slightly below the point where you can't do strong field QED calculations, so everything will be fine. But if you want to push this further, there's completely new calculational techniques which have to be developed in order to understand anything that's going on.
But this would be true of any electron collider.
Not necessarily. So for
Why
example,
is it
click
forced
ILC.
to be so high for Wakefield?
So it's partially this. So it's proportional to the energy.
No,
So
you're right, I mean, it's not intrinsic to the Wakefield-ness.
that's true. Yeah.
It's just a problem with,
It's just the problem of the actual collision.
so if you want to do an E plus E minus collider, I guess, is it just that the cross-section is so small?
Well, if you had a higher number of electrons in your bunch, right? If you had more electrons in your bunch, then they could be more dispersed. But because plasma, the Wakefield has such a small spot, it doesn't get very many electrons, so they have to be really, really bunched up. So
It's the denominator which kills you.
it's the denominator which is killing you, yeah.
But is this a much different problem than like colliding protons and having to worry about gluons interacting? Like, it just gets some additional like photon interaction can account for. Right?
It's similar, yeah. So what I'll show it in a little bit, it'll actually be very analogous to, for example, the PDFs that you see in proton-proton collisions, to describe it mathematically.
You're saying that it's a technology of the Wakefield acceleration that forces the denominator, not a demand for the luminosity.
So if I were to compare it to the closest collider, which is CLIC, running at 3,000
For example,
GeV,
right.
for example, the main benefit that CLIC has is they're using radio frequency cavities, so there's no limit on the frequency, or at least you can have a much higher frequency. So that allows you to have maybe a smaller number of particles per bunch, as well as maybe potentially increasing the transverse direction. The other thing you can do, and this will be important for later in my talk, is notice that the luminosity is proportional to the inverse power of the product of the transverse directions, while the beamstrahlung parameter is inversely proportional to the sum of the transverse directions. So what you can do is you can actually make the beam flat at the collision point, and this will reduce the beamstrahlung effect, but keep the geometric luminosity large. So this is one way that CLIC or the ILC have proposed to get around this to some degree. So there's lots of things you can do at CLIC and ILC to ignore or remove this effect, or at least maybe I should say reduce the effect of beamstrahlung. But At a Wakefield collider, there's just no way you can get around it. It's going to be a huge effect.
But like, why do you necessarily want to get rid of it, right? It is happening at the point of collision. It's some like really high energy event. Couldn't you get interesting physics out of the beamstrahlung itself?
That will be most of my talk.
Okay. Okay.
Yes. So typically, as you say, typically, as I said, this is considered as a bad thing. But exactly as you say, as you have perceived, this can be a very interesting thing. And so I'll go into some of the aspects of that in just a little bit. Okay. So, okay, there's many challenges. I won't discuss the first 3 challenges because they're not my expertise at all. The last 2 challenges, whether you should have positrons or not, and whether beamstrahlung is a significant detriment or a positive aspect, I will try to discuss in my talk. And first off, let me just quickly discuss positron acceleration. Whether you can do positron acceleration is a question that's not for me, but one question I can answer is, maybe I should say, what is the benefit or loss of not being able to have positrons? And in order to answer this question, I have to give you what are the possibilities. So the possibilities are maybe R&D makes a breakthrough, you can accelerate positrons just as easy as electrons. Maybe you can accelerate positrons but with lower luminosity, at which point the question is, what is the loss in terms of effective luminosity for a given collision or a process that you're interested in if you don't have positrons? And then the third possibility is that positrons simply cannot be accelerated, in which case you're stuck with an electron-electron collider, which may or may not be interesting. And one thing you can do is you can actually build a photon-photon collider from the electron-electron collider. So I'm not sure if anyone has heard of a photon-photon collider before in this audience. It's an extremely interesting possibility, and it's actually not so complicated. If you have well, I shouldn't say that. It's not so complicated for a theorist, let's say it that way. If you have 2 electron beams, you can send them towards each other and shine a laser at the electron beams right before the interaction point, and the photons will backscatter off of the electrons through this U-channel process in exactly the opposite direction, and they will have exactly the same energy as or maybe I should say roughly the same energy as the incoming electrons. So you can turn a 10 TeV, E-E- collider, into a photon-photon collider. And then the question is that interesting or not? Do you want to build a photon-photon collider, or do you want to stick with an E-E- collider? So all of these questions have to be taken under consideration when discussing which future colliders are most interesting for different physics opportunities.
Why does it have to be a photon at these energies? What's the center of mass energy going to be between the laser and the electron? I'm saying if the center mass energy is between the photon and the electron were high enough, couldn't you then have, you can make its E gamma to, say, nu W or to EZ?
So typically, the center mass energy is not actually that high.
Okay.
So the photons are coming from X-rays, so they have typically an energy of an EV or so, few EV. I think for this proposal, it's like 3 EV. And if you look at the center mass energy, it's actually not at a scale where you're going to be producing Z bosons or anything like that. It's much smaller than that. But I think that's an interesting question. I don't know. Okay, but so then the other question, so that's the general idea with positrons. One of the aspects I'll be interested in my talk is what is the overall benefit of having different collider beams? And I want to compare them all for different for different new physics searches. And at the end of the day, I kind of think of it in terms of the luminosity that's required in order to achieve a certain new physics target.
But with photons, presumably you also don't have this beamstrahlung problem, right?
In fact, you do.
You do?
Yeah, so you don't get around this.
So it's the same. It doesn't matter.
Yeah, and so I'll show that in a little bit.
Okay, thanks.
Okay, but then let me talk about beamstrahlung now. So the way I'll describe beamstrahlung is with luminosity spectra. So a lot of times when we talk about luminosity, we think about a single number, right? And we can describe the number in terms of the geometric quantities of the beams that are colliding. But when you have large beamstrahlung, what happens is at the collision point, there's lots of interactions between the 2 different beams, which can produce, for example, photons from the interaction. These photons will in general be in the exact same direction as the beams, so they'll be going along beam direction. And they can follow up in secondary collisions. The way I've drawn it here, it doesn't look like it'll collide, but in general, the photons that appear at the beginning of the collision of the two beams can eventually collide further on along the beam. You can also, instead of producing photons, produce electrons and positrons, and these can also collide later on in the beam. And this is very similar to initial state radiation, except initial state radiation is a microscopic quantity, whereas these are all mesoscopic, happening on the length scale of the actual bunches, which is of order microns. Okay. But the way that you can describe these effects is with the luminosity spectra. So instead of considering luminosity as one single number, we'll consider it as the luminosity, sorry, this is supposed to show up now, but the luminosity for given interactions of a certain center mass energy. And if you have an E minus E minus collider with no beamstrahlung, you would still have initial state radiation, because that's just a microscopic quantity of the collision. And that can give you different center mass energies for the colliding electrons and positrons, which would look something like this. When you include beamstrahlung, and you have, let's say, a perfectly round Gaussian beam, you would bump this up to this point here on this brown line, and this can increase the collisions at a certain energy, for example, like 1 TeV, by roughly 3 orders of magnitude. You can flatten the beam and decrease the amount of beamstrahlung, and this will decrease the luminosity at a given energy. For example, like 1 GeV, it decreases by roughly an order of magnitude. However, you get more luminosity at the peak. So in this talk, I'll be using beam parameters, which were determined by the LBNL group and some others, which there's 10 to the 9 particles in each bunch. The transverse direction is roughly 10 microns. And the transverse directions are either 1.5 nanometers for a round beam, or for a flat beam, 6 and 0.4 nanometers in the x and y direction, respectively. Additionally, I'll be assuming a geometric instantaneous luminosity, which is determined just by the beam geometry of roughly 7.5 inverse autobarns per year, which would allow you to be comparable to, for example, a muon collider with a similar 10 dB energy. It should be pointed out that these are all aspirational quantities, but it's kind of a requirement in order to see new physics that you need such geometric instantaneous luminosities. Simply because the cross-section falls off like 1 over energy squared, and if you want to see 10 dB new physics, you need to have a luminosity of this order of magnitude. Okay, so this is the luminosity spectra for E plus E minus collisions, and I mentioned it gets enhanced relative to the initial state radiation effect. But you also get collisions of E plus E minus, even from E minus E minus colliders. So if you have an E minus E minus collider, even though you don't have positrons in your beams, you produce positrons from the beamstrahlung effect, which can then collide and give you a luminosity spectra for E plus E minus collisions, which look something like this. So you don't have a lot of weight at the highest possible energies, but you have a fair amount of weight at lower energies. Additionally, for a gamma-gamma collider, there is beamstrahlung. It is a large effect. And you get an E plus E minus luminosity spectrum that looks something like this orange line. But then the question is, as you mentioned before, does this actually help, or is this just a hindrance in searching for new physics?
Why there are no muons there? Because your energies are huge. Wouldn't you produce muons as efficiently as electron positrons?
I think so. I think
you
so.
are just ignoring them.
Well, so it hasn't been included in the simulation, but I think it does happen. I haven't calculated it, but it may actually be very interesting. You may even get taus. So I think there's a joke that when people start talking about muon colliders, some people in the audience will say, well, what about a tau collider or something like that? This may actually be a tau collider. The taus produced, if they are produced, would have a lifetime that's longer. Would have a.
But wouldn't it make this whole thing so messy that it becomes useless?
Not necessarily. So, just like with a proton-proton collision, you do lose some information about the longitudinal direction of the collision, simply because you're taking two partons and you don't know the momentum in the z direction of each of the two different partons going in the collision. But you can still learn, as we know from the LHC, very interesting physics from that. unlike LEP, where you do actually know the longitudinal momentum very well.
No, but sorry, but if you worry about towers, there are also mesons, right? You produce quark anti-quark pairs, right? So then it's,
Those are extended though.
but why does it matter? You produce quark anti-quark, they hadronize, right? If
I mean, isn't this at some point, like if I've got high energy photons coming in, then I've got some sort of like T-channel process where it goes photon to photon and I have a T-channel fermion, right?
Yeah.
Like that,
Yeah.
right? And that's going to be tau anti-tau, quark anti-quark. And what is going to happen is that at some point as this process becomes sort of softer, I should stop thinking of this as like a hard process, but I should start thinking of this as like some sort of like splitting function coming from the photon itself. And there's some way of separating that that's really technical and hard.
That's why it seems like you get a huge suppression from the mass. That's why I'm really surprised that you think that muons would be relevant.
Right. So there's a couple of effects, and so maybe I won't go into detail. We can discuss it later. But so the main production channel, for example, for E plus E minus, is actually when you have some sort of process which is like this. I'll just draw it like this. Okay. So it's a coherent interaction with the background electric field, which produces E plus E minus, with one hard photon. This is called nonlinear Bright-Wheeler. You also have a process, Schwinger pair production, where you produce the E plus E minus pair directly out of the vacuum, coherently. And then you also have processes that are incoherent, just you have Bright-Wheeler, something like this, two hard photons. This is the dominant process for E plus E minus production. This is, I think, a not irrelevant process. And through this process, you could definitely produce mu's and taus. They would be, as you mentioned, less than E plus E minus, but I don't know if it's negligible.
but what about quarks then?
That would be produced in the exact same way.
But isn't that a problem? Because then it's really become hadronic machine, right? If you
Well, except for that you're not coupling to those more strongly than you couple to the other fermions, right?
But that's not, so maybe I'm very, but there's nothing special about the plasmin that's in that kind of production process, right? What's special about
yeah, that's not in the plasma, right?
That's something,
But
but
special
that's a
about
vacuum,
plasma is
that's a
the beam.
vacuum property, it's not
No, but the beam is very dense here, right? That's a
Okay.
There's nothing with plasma here.
I guess it's the size, especially in that the size of the coherent field is huge.
right.
Like the background to the cross.
But that in the cross, but the other one, the
Oh,
the
the
one
other-
of the muon, it's another thing, like,
Right.
we don't worry about that so much in current colliders.
No, but because beam has different
It
properties.
is different, okay.
I mean, that's a gluon-gluon collision at the LHC,
Yeah.
but the point
Yeah.
is that quarks couple to gluons, and so they get lots of them, but everybody couples to electromagnetism roughly the same, so you're not going to favor
Yeah,
quarks
yeah,
over. So
exactly.
you still could have pretty clean signals, I would think.
Yeah.
It's not going to be a giant mess.
So maybe I won't go too much into it, but I do think it's an interesting question, and I don't think it's been fully answered. In
No,
fact,
but in fact you answered. You said this is dominant,
Yes.
so therefore we shouldn't worry too much about it.
The question is, what's the ratio?
yeah.
I would have thought
And
it
I
was
don't know what the
ratio
ratio
of
is.
masses or something.
In fact, in the simulations, these have not been included in the simulation so far. You can calculate them roughly by hand, and you can show that they're not so large as these. The coherent enhancement is pretty large. But I guess even if the E plus E minus is mu plus mu minus is down here or something like that. I don't know if that's interesting or not. It might be interesting, but I just don't know the answer. So maybe I won't.
But for quarks, because muon is like 100 MeV, quarks are much lighter, right? Because it doesn't matter that hadrons will be heavier.
Cute.
But then Len's point is correct, and you should never talk about those quarks, right? Then you should talk about the pions.
No, you first produce quarks and then they hadronize, right?
But that's only if you're already at a momentum
Sort of a
state which
quark
is already
plasma.
high enough
Yeah.
that you're above the QCD scale, right?
Yeah.
So then
I
I'm
see.
already in a kinematic regime where they don't matter, and if I'm in a kinematic regime where they do matter, I should be talking about pions. So
Mm.
Okay, but maybe I'll just continue on. So the question is, does this actually help? So one way I like to think about this is in terms of the following ratio. And I think this actually explains the entire rest of my talk, more or less. I think this slide is important. So I can describe the ratio of E plus E minus collisions producing a certain final state, let me call it script F, with threshold mass m sub F. Sorry, I don't know if I said this right. So I can describe it as the ratio of production via beamstrahlung to to the production via initial state radiation that you would have at a machine without beamstrahlung. Okay? So this is basically the beamstrahlung enhancement ratio. And if I take a cross-section, which is proportional to S, say for example, some flavor violating process from higher dimensional operators, then what you find is that for a given threshold mass, this ratio, this beamstrahlung enhancement ratio, is not very large. It's of order 1, even for low masses. And it's bad if you're looking for heavy threshold particles. If instead I'm looking for a process that is logarithmically enhanced, something like vector boson fusion, I can get enhancement as large as roughly order 10 at low threshold masses. So for example, if I want to produce a Higgs or a di-Higgs event using vector boson fusion, beamstrahlung will enhance this production by roughly an order of magnitude. Then, if I'm looking for a process that goes like 1 over energy squared, you see that the enhancement grows significantly for lower masses. And then finally, as the extreme example, if I consider a resonance production with a parton cross-section that looks like a delta function, I can get many orders of magnitude of enhancement throughout the entire mass range. Okay? So I would argue that the type of process which is maximally enhanced from beamstrahlung is resonance production.
So does that depend on the width of the resonance?
No, so I mean, this would be a narrow width approximation type thing. So it doesn't depend on, I mean, the width would cancel out in this ratio, if that makes sense. Okay. Good. So I'm going to discuss 2 different projects that I'm looking at the moment. And I'll try to be a little bit quick on this because I don't think the details are necessarily as interesting as the physics results. But I'll first consider Higgs production, which as I mentioned is essentially through vector boson fusion, and then I'll discuss searches for heavy resonances. So I don't think I need to convince the audience that Higgs is an interesting particle and needs to be measured better than it currently is, and that there's many possible aspects of the Higgs which could lead to interesting new physics. But the important point that I want to emphasize, and this has been emphasized before in the literature, is that higher energy actually means higher statistics for Higgs physics. So a very simple kind of classical analogy that you can use to understand this is that if I have, for example, Z boson fusion of a Higgs, then a process which looks something like this, at low energy the electrons don't get very close to each other, and so the Z field, the effective Z field, is not very large in this region. But if I increase the energy, if I increase the energy, then the Z field gets significantly stronger because the electrons get closer to each other, and this increases the rate at which you produce the Higgs. That's just the analogy that you can have to understand why this effect gets larger. But let me just show you the cross-sections because that's all that really matters at the end of the day. The associated production, not through vector boson fusion, but through this S-channel process, dies like 1 over S, as it must. But vector boson fusion of a Higgs grows logarithmically as a function of the center mass energy. Okay. So this process here, this is for a final state with 2 neutrinos. This would be through W boson fusion. And this orange line is from Z boson fusion of a Higgs. If I'm looking for di-Higgs, for example, if I care about the Higgs self-interaction, then my options are limited to associated production, which would look something like this and is much smaller in total cross-section and dies off like 1 over S. Or I can look for vector boson fusion, which again grows with energy. And the thing I want to emphasize is that as I go to very high energy, vector boson fusion is much, much larger than the associated production of the related channel. Okay. So high energy means that you can produce significantly more Higgses than you can with a low energy collider, potentially. One aspect I want to mention that's relevant for Wakefield colliders is that if I'm limited to only electrons, and I don't have positrons, then I lose out on W boson fusion, which is the dominant production mode of both Higgs and double Higgs events. So I lose roughly an order of magnitude in luminosity from not having positrons. And in fact, it's worse than this because the luminosity spectrum of these Wakefield beams is also significantly better for E plus E minus colliders. You can think of this basically as as one electron beam is passing by the positron beam, it gets sucked into the other beam and increases the effective luminosity, the total number of collisions. Whereas if I have two E- beams, they repel each other. So I actually lose almost another order of magnitude just from the luminosity spectra. I'll go through this a little bit quickly because this is just numbers at this point. But what I just mentioned, this is numerically the statement that flat beams lose roughly an order of magnitude relative to round beams. This is just from, oh, sorry, I said that wrong. If I don't have positrons, I lose roughly a factor of 30 in the total Higgs production. While if I don't have round beams, I lose a factor of 4. So flat beams are actually worse than round beams. In other words, this is going back to your point that beamstrahlung is actually a benefit for Higgs studies. The same thing is true for di-Higgs, so I won't go into that in great detail. But what I want to emphasize at this point is, at the end of the day, you can count the number of Higgs that you produce, and this is probably the most interesting measure that you can give for a Higgs study. But you can also ask the question, what can I do with this that's qualitatively new to something that, for example, the LHC could do? And one aspect that you can consider is the Higgs self-interaction. So that would be, that would show up in di-Higgs production, and you can see that by just measuring the cross-section. And the HLHC is expected to get to roughly 50% uncertainty in the Higgs self-interaction coupling. A 10 TeV muon collider can get to, get to roughly 5%, so a significant improvement. Then the question is, how well can a Wakefield collider do? For an E plus E minus round Wakefield collider with 10 inverse attobarns of luminosity, the same as a muon collider, you can do a little bit better, roughly maybe a factor of 2 better in both of the interactions. This interaction is the Higgs self-coupling. This is the interaction of 2 Higgses with 2 vector bosons. A flat beam does slightly worse, but still better than a Wakefield collider because it still has some beamstrahlung enhancement. An E minus E minus collider does quite poorly. So you lose out a lot if you only have electrons and not positrons. However, if you turn those electrons into photons, you actually do comparatively well. So this is from photons, and this is from E plus E minus, the blue curve here. And you see it's not as good, but it's still of roughly the same order of magnitude, so it's not so bad. And so if all you have is E minus minus, and you only care about Higgs physics, you can turn the E minus into a gamma collider, and then you can do fairly well. Okay, but let me get on to the resonance search, because I think this is really where a Wakefield collider benefits from beamstrahlung, and I think it's where it shows this effect most significantly. And I would like to, so this is work I've done with Toby Ufrakog and Massimo Cipresi. And Massimo is a grad student at CISA, and he's tremendous on this project, and I want to emphasize that he's the guy who did most of the work in this project. He's great. Okay, and so let me quickly discuss resonance searches in general. So if I want to produce a resonance, for example, this X particle here, which you can also think of as Z prime, then typically the dominant kinematics for this process is when one of these photons takes energy from this lepton, but is roughly collinear with the lepton. So it's ejected collinear to the electron here, such that you give this exactly the right amount of energy to be on shell. At the end of the day, you can describe this virtual lepton using parton distribution functions in the following way. So you can describe the collision energy using a parton luminosity function that looks like this. This describes the total number of collisions that happen at a given center of mass energy. And then the total cross-section is related to the parton level cross-section just by convolution with the parton luminosity function. For a resonance, this convolution is extremely simple. The cross-section looks like a delta function. And at the end of the day, the total cross-section for resonance production is just the product of this quantity here, which is just this cross-section here, times the luminosity function. If I want to turn this calculation, which is essentially for a muon collider, into a calculation for a Wakefield collider, all I need to do is I need to transform, I need to transform this parton luminosity function into the luminosity spectra of the Wakefield collider. And so here I'm just showing again the luminosity spectra of the Wakefield colliders for different Wakefield collider configurations. And the important bit here is that beamstrahlung is significantly larger than the parton luminosity functions. So here I'm showing the ratio of the beamstrahlung luminosity spectra to the parton luminosity function, which is orders of magnitude higher. Then there's some additional aspects of the actual analysis, which I'll go over very quickly. So it turns out that the resonance is produced with a particular rapidity just because it's most common for one of these electrons to lose one photon rather than both to lose a photon. So the boost of the collision or center mass energy is specified. So at the end of the day, if you're doing a search, you are searching, or you're doing a bump hunt in the invariant mass of the final state leptons, as well as the rapidity of the final state leptons. You can model the detector. It turns out if you're doing a muon collider and you're searching for an E plus E minus final state, the cuts that you apply are limited by the electron energy resolution, which is roughly 1% at these energies. And the backgrounds come from the exact same signal process where you replace the resonance with a off-shell photon or Z. There's also additional background from vector boson fusion, which you can remove by cutting on the rapidity. So this is all details. It's not super interesting. But at the end of the day, if this is the LHC constraints on the example of a simple kinetically mixed dark photon, the muon collider search, the one that I was just mentioning, can give you constraints that look something like this. So it can significantly improve upon the LHC bounds that are currently there. It also outperforms, for example, the FCCHH, which is quite interesting as well. But this is a muon collider, and I want to discuss Wakefield colliders, so let me get to that now. What changes with a Wakefield collider? Well, one thing that changes, which is non-trivial, is the rapidity. So I mentioned before that if I'm doing a muon collider, the dominant process is when one of the muons releases one initial state radiation photon to fix the rapidity. So the rapidity distribution for a muon collider would look something like this orange curve here. And if you cut on the edges, you lose basically none of the signal. However, for a Wakefield collider, the rapidity distribution is significantly broader, and if you were to try to cut, you would lose roughly 50% or more of the signal. And so you essentially never want to cut on the rapidity. So you lose out on the rapidity cut, and effectively what that modifies is that your background is no longer the irreducible background from replacing the resonance with an off-shell gamma or Z, but it's actually the background coming from when you have two photons producing a dilepton pair, which you mistake as the Z prime. But at the end of the day, here's the constraints that you would get. If I have an E plus E minus round Wakefield collider with 10 inverse attobarns of geometric luminosity, I would be able to constrain this entire region here. And if I have a flat collider, I lose sensitivity just by a little bit, and I would be down here. But this is, of course, if I'm assuming that I have positrons. If I don't, it's actually not so bad for resonance searches. So this, I think, really shows the nice aspect of Wakefield colliders is that even if you don't have positrons, you create positrons from the beamstrahlung itself, and you can actually be competitive. So you outperform, for example, the HLHC throughout this entire region here, even without positrons. If I convert the E minus E minus into a gamma-gamma collider, I don't see the same size of improvement that I saw in the Higgs search, but I do get a pretty good collider as well for resonance searches. But this kind of makes sense, right? If I have a gamma-gamma collider, I need to produce both an E plus and an E minus to find the Z prime. So it's not quite as ideal as if I'm doing a Higgs search. Just to give you some reference, if I consider a one-loop induced kinetic mixing through some new physics showing up in a loop like this, connecting our photon with a dark Z prime, and I assume that the dark gauge coupling is of order 0.5 to 4 pi, then I would expect to be in this regime here, this magenta band. And I think one relevant question for any search for Z primes is, or kinetically mixed Z primes, is how much of this pink band do you actually remove or constrain or potentially discover? And as you can see, the Wakefield collider does pretty well throughout this entire region. One other thing that I want to mention is that right now, I cut this off at roughly 500 GeV. That's only because our simulations only go down to 500 GeV. In theory, this doesn't cut off at 500 GeV, it goes further. We just don't have the simulation for that. So I'd be interested to see how far this goes down to lower masses, because in theory, nothing says that the kinetically mixed Z prime has to be very heavy. It could be quite light, and I don't know what the answer for that is at this point.
This is mixing with hypercharge.
Yeah, with hypercharge. Okay, so let me just quickly flash some additional analyses which are being done at the moment. So there's a paper out on searching for WIMPs by these folk here, which is very nice. This is a really interesting paper. This is an example of a 1/S cross-section where you can get pretty large enhancement from beamstrahlung. There's also a paper looking at the production of a scalar singlet, as well as lepton flavor violation. Maybe I'll just mention some future work in open problems. So one thing that I think is the most obvious thing to do to extend this is to look for particles or resonance particles coupled to photons. These Wakefield colliders are also very, very impressive gamma-gamma colliders, as I mentioned before, and the enhancement ratio for gamma-gamma collisions is many orders of magnitude, or maybe I should say, a few orders of magnitude.
Sorry, isn't the main open problem to build a Wakefield collider first?
Yes. Yeah. So that's okay. So this is in the order of things I can do, realistically. So, okay, you're skipping. So this is the simplest thing you can do. The second thing I'd be very interested in is coherent production of an axion through a process similar to the nonlinear Bright-Wheeler process that I was mentioned before. And as I said over here, this is the dominant process for E plus E minus production, so it should also be the dominant production for axions. Third, so this is going in order of difficulty as well. Third is extending the Rittis-Narajny conjecture, or limit. So if you do strong field QED, you can resum the interaction of the background electric field to give you a dressed propagator that looks like this. And when you do that and you calculate loops, you find that the loops, the perturbative expansion parameter, is alpha times the beamstrahlung parameter to the 2/3 power. In other words, strong field QED completely breaks down as a calculational technique when your beamstrahlung parameter is larger than 1,000. Nobody knows how to go beyond this. Luckily, the simulations I use a beamstrahlung parameter of, I think, 300, so they're probably reliable, but there's probably corrections, and no one knows what those corrections are.
Sorry, did you say for a real Wakefield it will be 10 to the 5 is chi? Sorry, what's the
So
value of
that
chi?
was the 10 to the 5 was with the generic numbers that I used.
Oh, okay.
But this is not those generic numbers. So the simulation uses different numbers.
I guess I'm asking for if a real Wakefield collider is built, what is the chi value?
Nobody knows.
Oh,
Well, I mean, I would say it's actually interesting to go above this.
right.
It would mean that you don't necessarily know how to calculate things, which would be a problem, because if you don't know the luminosity spectra,
Yeah.
then that's also a problem.
Right.
You'd have to be able to measure it somehow. And maybe you can measure it, for example, by doing Baba scattering. This is the way we normally measure luminosity on E plus E minus collider. But now you have to measure it at every single energy. And I don't know if that's feasible or not.
Is there any hope of having a theoretical framework for dealing with these strong fields? Or?
I think so. I mean, so this was work done in the 70s.
Yeah.
So it's very impressive, but I think they saw this number and they said, well, we're fine. But
There must be a way of extending it.
I mean, if you can resum these loops, then maybe it's okay. I don't know. And fourth, which is, as you mentioned, finding Wakefield colliders that actually work. And so this involves probably doing simulations of plasmas and finding configurations of the plasma and the beams that you inject in order to actually make this feasible. This is a very hard question, though. And, I don't know if I'm the person for number 4, but I think this is the most important thing that someone can do, and I think it is
Are
something
people
worth it.
actually doing it?
Yes, yes. Many people are doing it, in fact. but it's extremely challenging. But as I said before, there's many national labs. There's actual Wakefield accelerators being built at SLAC, at DESY, at CERN right now, using different methods, at LBNL. And, but nobody knows how to overcome several of these really difficult challenges. Maybe I shouldn't say they don't know how. I think it's hard. And they're doing very impressive work, but it's still a far future thing, which requires a lot of R&D. Okay, so maybe I won't do the conclusion because I think I'm over time, but I think it's all very exciting, and I think there's some interesting things to be explored with Wakefield colliders. All options, I think, at the end of the day need to be understood, and the benefits of different options also need to be compared to each other. And Wakefield colliders, even though they're not maybe as flashy as muon colliders and haven't gotten as much attention, I think they're a very interesting possibility, and I hope you found it so as well. All right, thank you.
I know how off-shell, well, I kind of know how off-shell a muon collider is. How off-shell is this?
I think, well, okay, I don't know the exact answer to that, but similarly off-shell.
Similarly?
Yeah, but I don't know if, I mean, the positron acceleration problem I think is really challenging. I don't know how feasible it is to accelerate positrons. But I think
you convinced me the gamma-gamma collider is interesting, so I'm willing to give you that.
Okay.
So that's all I'm asking for is for you to build the gamma-gamma collider.
Yeah, but I think the other challenging thing is politics as well, and I have no idea how off-shell that is.
I just mean from when you hear the muon collider people talk, they're like, oh, we have a set of like concrete engineering problems, and we have ideas of how to do them, and we think that if you sort of like forecast, we'll have solved these problems by the time that you're actually, digging a tunnel. I don't have a sense in this as to whether the problems are similar, I mean, it's clear you showed some plots of the improvements in some of the specs that you need but is that something where you just they just keep doing what they're doing, then you'll keep improving these things in some Moore's Law fashion, and eventually they'll get to where they need, or there are some like clear big technical things they need to solve first?
I don't know if I can answer that very definitively. I know there's many challenges, and I know the positron one is extremely challenging, but I don't know why the other ones are impossible to overcome.
Yeah, because I've already told you I'm happy with the photon-photon collider.
Okay.
That you convinced me is an interesting thing, and if you can get to these energies and do photon collisions, I'm delighted. But
you could aim your Wakefield electrons at the positrons that's in an E plus E minus collider, that use defunct E plus E minus collider.
Yeah, I mean, so it's kind of an interesting aspect that it turns out it's easier to cool mu pluses, and it's easier to accelerate E minuses with Wakefield colliders. So I don't think it's a good idea, but you could do a mu minus E plus accelerator, which is asymmetric. But I think one of the main challenges is that people want to actually develop a first step in Wakefield accelerators that actually does some interesting physics. And there is one proposal. It's called HEP, the highly asymmetric linear Higgs factory, and it's an E minus accelerator through Wakefield accelerators and an E plus accelerator through radio frequency cavities. And you can get the E plus to roughly 50 GeV and the E minus to 500 GeV, and it turns out this is exactly what you need in order to produce a Higgs. So this is one proposal by mostly Germans and I think some people in Oxford for a linear Higgs factory using Wakefield technology.
This is ZH? This is the ZH?
Yeah, at the ZH energy.
So you're arguing that this beamstrahlung, this actually can be a good thing. So can one then try to modify conventional beams without going to Wakefield, but just take conventional plus and minus and spoil the beam such that to enhance beamstrahlung and get something out of it?
So in theory, yes, but it's the parameters that I mentioned are extremely hard to achieve. So the nanometer transverse size is actually not crazy. Bell 2 is trying to achieve this right now, but as you know, Bell 2 is having some trouble getting the intended instantaneous luminosity that they want. But the energy is really the main thing here, as well as the number of particles per bunch. So I don't know if they can. But it would be very interesting just to measure strong field QED, for example.
Right.
Nothing is able to get to these electric field sizes, or even close.
Any more questions for Kevin? Just thinking again.
Well, that was fun, thank you.